work done by an action agent. Work done by action agent in constructing a charged system will be available as electrostatic field energy in electrostatic field in the system. I'll write it. This electrostatic field energy is called as the self energy of a system. Okay, let me begin with, I want to construct a thin uniformly charged shell. So thin uniformly charged shell. So first, actually, this is the shell, no? So whatever the charge on it initially, there won't be any charge. Then how to make it charged here? For that, what happens? The action agent has to do work. He has to do work. So it will be like this. So first, this is the neutral thin conducting shell. I'll write it air, this air, and this iron or any metal. So initially there's no charge. Then some action agent. So what you do is going to do work to bring this charge system, and finally what happens? It will acquire a charge. Let me keep it here. Yeah, we'll get into this one. So now, so this action agent, okay, we'll put a charge dq. So after keep on adding a charge dq. So what is the charge on this? Okay, let it have a charge q here. So how this charge q has come? Because action agent has added a charge dq amount of charge continuously, and it has acquired a charge plus q. Next, what he'll do is, like, an action agent is there, is at infinity, and he will carry a charge dq, and he will move slowly. Then he will add the charge dq to the system. Like that, when he keeps on adds charge, you will at infinity some charge will be there. That charge, what when he will take, will move slowly, then he'll come and add to the, it will give to the conducting shell. Where do the charge will reside only on the surface. Like that, he has to do work, and finally what happened? The system has acquired a charge. How much? Finally it has acquired a charge capital Q. No, I had to do work. No, see, all of a sudden I can't bring the charge capital Q. I had to add small elemental charges. When I keep on add elemental charges, then the amount of charge in that will increase and finally become capital Q. It's like simple. You may find this very difficult. Okay, I want to fill up this bucket. I'll give a spoon. Okay, in that you fill up water. So that elemental, the amount of water present in spoon will become dq. I'll okay, from infinity, okay, I'll ask you to go to the ocean or sea. From there, bring water in a spoon and fill up in a bucket. So all of a sudden, will you fill up? All of a sudden, will you get water in the bucket? No. So the amount of water will keep on increase. When you add each spoons like this, every time you have to do work, no? The same thing here. So the charge plus Q will not come all of a sudden. Elemental charges dq, when I keep on add, earlier it was 0, now it has become finally plus Q. Okay, how to find out that mechanical work then? And I'll be doing work. what all I do mechanical work, that will be converted into electrostatic field energy. And where it will be there surrounding the charge, that one. Okay, let's get into the work done by extra agent. So what we have to do is work done by extra agent in moving a charge dq from infinity to point P. Let me write here this one. So that should be equal to dq into potential difference. How you write potential difference? Vp minus V infinity. Can you remember electrostatic? This one, dq is a charge which extra agent is going to move it, and it's going to put on the shell. What is the potential on the shell at point P? I have to show on the surface, no? Yeah. We'll take like this here. So what is the expression now? So this should be equal to dq. Potential on the surface of a shell, how much it should be, because already is having some charge, kqr, minus potential at infinity due to this will be 0. No, this will become k by r integral of q dq. Now tell me, like finally it was 0. The amount of charge on shell was 0. Now finally it is acquired capital Q. So the limits will become 0 to capital Q. So how much will get? Kq square by 2r. So this is nothing but, now where do this energy gone? Next question. We are going to ask us. So the excitation did work to charge a shell. Where do this energy gone? This energy will be converted, will be available as electrostatic field energies in a charged system. So this is nothing but self energy. I'll write it. Where it is available, where the electrostatic field is present, there the self energy will be there. Electrostatic field energy, where it is present. Okay, we know where all electrostatic field is there, that will be present. So here it will be. Let me show that field lines. Where it is surrounding that one. Will it there be inside? No, it will be there only from the surface to the shell. Till where it will be spreaded? It will be spreaded till infinity. So where the self energy, so where the electrostatic field energy will be there from the surface to infinity of a conducting shell, the electrostatic field energy will be present. Able to understand this one? I think you have to remember formula, very important, kq square by 2r. Now, can we solve by any other method? Yes, we can also use by other method. What is the other method? Here, what I suggest is like instead of this, you can take help of this one. So as you may, already is there, no? Okay, we'll take this one. Here, I'll ask you to assume a shell, a thin shell of radius r, thickness dr. There's like a thin shell. Okay, shall you write it? Shall we calculate? Can you remember electrostatic energy density formula? First, let me calculate how much of energy present in this. So what is du? Now, what is the electric field at a distance r? Anybody due to thin charge shell? So it should be equal to k q by r square. Then what is the energy density there? Half epsilon naught e square. So this should be equal to half epsilon naught kq by r square whole square. So this will become so k 1 epsilon. Okay, let me retain this one, no problem. K square q square by 2 r to power of 4. This is the expression for energy density. Am I right? Now, can we calculate how much of energy present in this shell? energy in the elemental shell. Du is equal to, this is the elemental shell, is equal to energy density into volume. What is a F naught K square Q square 2R to power 4? What is the volume of this? This should be equal to 4 pi R square dr, not 4 by 3 pi R cube. How much of energy present in this green color region? That is du. Don't write this volume. Fine. Now this will be further simplification. 4 pi epsilon naught K square Q square 2 R to power of 4 2R square will be there, and this is dr. 4 pi f naught, 1 will cancel out. So K Q square by 2, let me keep outside. So this will be R to power of minus 2 dr. From where to where the field is present? From capital R to small r, infinity. This is nothing but self energy. Sir, I didn't like the work done. Okay, fine, sir, you explained nicely, but I didn't like the work done. Okay, you know energy density formula, because what is the self-energy definition? Work done by external agent in constructing a charge system will be available as electrostatic field energy in a charged system. That electrostatic field energy is self-energy. Can we calculate how much of electrostatic field energy is present? Electrostatic field energy present due to a charged conducting shell, because the field is present from surface of the shell to till infinity. The field is present. So first I'll assume a elemental shell of radius r, thickness dr. I'll first calculate how much of energy present in that shell. Then I'll integrate from capital R to infinity. I'll get the total field energy present in a due to a charged shell. I got the same answer. That's what the meaning here. Able to understand the self-energy idea? This one? To construct any charge system, we have to do mechanical work. That mechanical work will be converted as self-energy of a system. On its own, the charge